Welcome to the next episode of Thermodynamics. Today you are going to learn about heat and changes of state of matter. Heat is energy which is transferred from one to another system because of difference in temperature. It is denoted with big Q and is measured in joules, big J, since it is a form of energy. It is thermal energy. So we have that heat is marked with big Q and is measured in joules, big J. Joule is its measuring unit. It is normally transferred from a warmer to a colder body in one of the next three ways: conduction, convection, and radiation. Conduction is heat transfer common to solid bodies because it occurs as heat transfer between two molecules which collide. Convection is typical for fluids where intermolecular forces are weaker, and this transfer happens when fluids molecules change their position in space. In radiation, heat is transferred by photons through electromagnetic radiation. Calorimetry is a branch of physics which measures quantity of heat exchanged between bodies. Calorimeter is an object used for many things, such as measuring amount of energy released from an exothermic chemical reaction or determining matter-specific heat capacity. One of the types of calorimeter is a bomb calorimeter, used for measuring heat of combustion of a particular chemical reaction. One of the basic calorimetric formulas which allows these calculations is this one, that Q is equal to mc delta T. One of the basic formulas in calorimetry. Where Q is heat, m is mass of a system, c is specific heat capacity, and delta T is change in temperature expressed in kelvins or even in degrees of Celsius, since we have said that the difference of temperature in kelvins is equal to that in degrees of Celsius. Specific heat capacity, small c, is an amount of heat needed to increase temperature of a matter sample of mass unit m for temperature difference delta T, so we have expression for it derived from the first calorimetric formula, that small c, so this specific heat capacity, is Q over m delta T. So it is specific heat capacity and is marked with small c. So we have this formula, and we can see that it is measured in joules per kilograms Kelvin. There are two special types of specific heat capacity. First is heating at constant pressure, P, called Cp, and the other is heating at constant volume, Cv. So Cp, small c meaning specific heat capacity, P index for constant pressure, so this is specific heat capacity for constant pressure, and Cv, specific heat capacity for constant volume V. Gases have significant difference between these two, where this Cp for at constant pressure is much greater than this specific heat capacity at constant volume. This is relation which is for gases only, while solid bodies and liquids have that difference, but very little. There are also some other types of heat capacity other than specific heat capacity, small c, such as heat capacity, big C, which is proportion of amount of heat Q transferred to a body per change in temperature delta T. So we have that this big C, heat capacity, is change in heat, so heat over change in temperature delta T, and it is heat capacity. And its measuring unit, we can see that it is joules per Kelvin. so joules per Kelvin. Also, there is molar heat capacity, Cm, M meaning molar, which is an amount of heat needed to increase temperature of matter sample with amount of substance small n for temperature difference delta T. So we have very similar formula as that for specific heat capacity, but here we have dependence on amount of substance small n rather than on mass small m. So we have that molar heat capacity, big C small m, m index meaning molar, is proportion of Q, heat, over product of amount of substance and change in temperature. So it is molar heat capacity. And we can see that it is measured in joules per mole Kelvin. Molar heat capacity has two types similar to those of specific heat capacity. Molar heat capacity at constant pressure, so CPM, and molar heat capacity at constant volume, CPV. We can see that these are very similar to this for specific heat capacity. The second important formula, called calorimetric equation, is the next one, which describes heat transfer between two bodies, which occurs as long as their temperatures do not equalize. It is based on the law of conservation of energy, which says that energy cannot be either created or destroyed, so heat released from a body of higher temperature is equal to energy absorbed by a body of lower temperature. So Q released is equal to Q absorbed, where body of higher temperature releases and this heat is absorbed by the other body of lower temperature. This we have according to and thanks to conservation of energy law. And from this we get this formula, which we have that for T2 greater than T1. So we have M1 and C1, which are mass and specific heat capacity of the first body in a system, respectively, M2 and C2, which are same, but for the other body exchanging heat with this first one. T1 and T2 are initial temperatures of these two bodies, and T is final temperature of both the bodies after they come in heat equilibrium, that is, come to the same temperature. We can write this calorimetric equation in another ways, but in this way, as we have written it, the second body has greater temperature than the first one, so T2 is greater than T1. So for this T2 greater than T1, we have this relation. Matter is natural in one of three states of matter: solid, denoted with small s, liquid, small l, or gaseous, small g. These three are also called phases, which is named for a homogeneous amount of matter, which can be mechanically separated from a heterogeneous mixture. Let's draw a graph called phase diagram, which graphically represents dependence of pressure on temperature, so a PT graph. So let's first draw it and then discuss. On x-axis we have T temperature and on y-axis pressure P. Oh, this is a phase diagram. So you can see here three areas, S, L and G, and two marked points on it, point P and point C. On x-axis is temperature and on y-axis is pressure. The lines separate areas of phases, solid, liquid and gaseous. So we have the solid line drawn, solid line, so this line, between solid and liquid phase, which represents melting, it as freezing point, since it is transition from solid to liquid, or from liquid to solid phase. Or so. Then the second line we have is this dashed line, which is between liquid and gas phase, and it represents boiling and condensation, because it is transition from liquid to gas or from gaseous to liquid state of matter. And finally this dotted line, which is line of sublimation and resublimation, which is transition from solid to gaseous and from gaseous to solid state of matter respectively. We also have here two very specific points. The first one is triple point, which is here marked as point T. Triple point is point where all three phases can coexist. The other point, which is indicated in this diagram, is critical point, point C, which includes critical temperature and critical pressure at which phase boundaries disappear. This phase diagram shown is phase diagram of water. What is interesting about it, so about this very phase diagram, is that the melting point line, so this one here, between solid and liquid, liquid and solid, melting it as freezing point line, is here has a shape of a decreasing function. This means that the lowest temperature where the liquid phase of water can exist decreases as temperature increases. So temperature decreases and pressure is increased. Unlike most other substances which have triple point temperature as the lowest temperature at which liquid phase can exist, meaning that this phase transition from solid to liquid, it is from liquid to solid, is graph of an increasing function for those other substances. When a matter is transformed from one state of matter to another, its temperature does not change, because all of the heat is spent on this transformation, and this heat needed for transition from one to another state of matter at constant temperature is called latent heat. So big QL, latent heat. Heat is Q and L meaning latent. And latent heat. So latent heat is this heat we have to spend on going from one to the other state of matter. There are also specific latent heat of melting, Lm. So specific latent heat of melting, and Lb, which is specific latent heat of boiling, which are characteristics of a material. Latent heat of melting, QLM, is a product of a material specific latent heat of melting, Lm, and its mass m. So QLM, latent heat of melting, is its mass m times specific latent heat of melting. And the same thing, so similarly we have that latent heat for of boiling, QLB, is product of a material specific latent heat of boiling and its mass, so m times Lb. We have similar expression. We have also heat of combustion, Q combustion, which is total energy released in form of a heat when a certain mass of a matter is combusted with oxygen under standard conditions. It is a product, so Q combustion is a product of matter mass times its specific combustion heat, marked with small r, so-called calorific value. So this small r is calorific value, which is used to express this heat of combustion is used to express calorific value of matter such as food or coal. That's all for today. Now you can take a quiz to test what you've learned today. The link you can find in the description of the video. Thanks for watching and stay with us.